Alright, welcome back, and we will continue our discussion about this Bernoulli's equation. What I was saying earlier is that the Bernoulli's equation can be expressed in terms of the energy form, where all the units is there in specific energy, or the meter squared per second squared, and then the Bernoulli's equation can also be expressed in terms of the head form. Okay, so for the head form, the unit is just in meters, and another expression is the pressure form, where the unit is just in pascals. Now, I was saying that this head form, in this head form, there's all it's also common to use the graphical representation, but I guess energy grade line. But I guess this will be more appropriate to discuss in details in our next topic. It's just that I just realized that when you draw the energy grade line, although it's still the same, you still have to consider the losses. Okay, so for example, you have let's say you have a conduit right here. Let's say this is our center line. Let's say this is our point 1, and in this point 1 we attach a piezometer, and in point 2 we attach also another piezometer. Okay, so at some reference point, let's say this is our arbitrary datum. If this is our point 1, this will be our point 2, then recall that when that the expression, I mean that this equation, Bernoulli's equation, says that the total energy is just constant, or it's just the same. In terms of head form, the energy grade line is actually the line that's connecting the total head of point 1 to the total head of point 2, without considering yet the losses. Okay, so the distance from the reference datum to let's say the center line, that's what we call that's our elevation head. And then from this point to the rise of the fluid in the piezometer, that's our pressure head. And then to some arbitrary let's say arbitrary point, that's going to be our velocity head, v1 squared all over 2g. So here we'll also have v1 squared all over 2g, and then the pressure head as well, for example. So we have the v2 squared all over 2g, and then the pressure head, that's p sub 2 all over the unit weight, and then let's say this is our elevation head. Okay, so the line that connects this point to this point is what we call the energy grade line. Okay, so that's basically the total head, and then plus the total head at point 1. Then this will represent the total head at point 2. Okay, anyway, if we consider frictions and other losses, then of course they're not going to be equal, because there are some dissipated energy at this point, because throughout the flow there's going to be frictions on the wall and other losses. So I guess this concept we'll just talk this in detail. We'll talk about this in detail in the next topic about conservation laws. Okay, now let's talk about the application of the Bernoulli's equation. Typical applications of the Bernoulli equation is, for example, let's write first here applications, or some applications. For example, we have a tank or a vessel, and then this vessel, for example, is filled with the fluid, and then you want to determine the velocity. Okay, if we have a tap right here, or a hole or an orifice, then of course the water would start to flow out. Okay, so sometimes we want to know the velocity at this point. Okay, so what is the velocity at this point? So if we let this location, or this point is point, or as point 2, and then at some reference, in order to apply the Bernoulli's equation, you need also another point, right? And we want a point wherein we have we can obtain values already. So one way is just to assume another point from this reference, from this free surface. Okay, so let's say this is our point 1. Okay, so if we apply our Bernoulli's equation, recall that the Bernoulli's equation, always remember that the Bernoulli's equation only applies to inviscid flows. That means that that the fluid is not viscous, or we don't take into consideration the viscous effects or the frictions, or let's just write no frictions, or ideal fluids. Okay, so just remember that Bernoulli's equation is only applicable for inviscid flows. Steady flows, that means that velocity does not change with time, or the properties as a whole does not change with time. Okay, so recall that when we talk about the steady flow, we're referring to something like you're taking a snapshot. Okay, so at that instant you took a snapshot on the let's say on the streamlines. Then after some time you take another snapshot, and then if you notice that there's no changes in the streamline, then we can say that the properties, they're not changing with time, and therefore the flow is said to be steady. Okay, so Bernoulli's equation, inviscid flow, steady flow, and incompressible fluids. Okay, so incompressible fluids, meaning that the density is constant. So why is it important to highlight this? It's simply because we derive the Bernoulli's equation, as we have already mentioned in the previous video, that the Bernoulli's equation is an integration of the Euler's differential equation for fluid motion along the streamline. Okay, so if these conditions are not met, then we cannot apply the Bernoulli's equation. Or if we apply the Bernoulli's equation, then we would result to erroneous answers. Okay, so now for the applications, then typical applications of the Bernoulli equations is, for example, we have this tank, and then we have the tank is filled with fluids. Then we drilled a hole right here, and we want to determine the velocity at this point. Okay, so if this is the streamline, then recall that for the Bernoulli equation to be applied, we need 2 points, right? The point 1 and point 2, and we want a point wherein we know some values already regarding the pressure or the velocity or the elevations. Okay, so in applying this, if we write the Bernoulli's equation, we have P1 by rho g plus z sub 1 plus v1 squared all over 2g is equal to the point 2, the heads at point 2. So rho g plus z sub 2 okay, plus v2 squared all over 2g. Okay, so that's the expression of the Bernoulli equation. Okay, so there are actually assumptions somehow depending upon the applications, but in these applications, for example, we have a large tank. The area of the tank is way larger as compared to the, let's say, to the area in this hole. Then the assumption is that the velocity right here, the velocity here is 0. Okay, so that's a typical example. Okay, what else? If this is 0, then in terms of gauge pressure, right? So this point 1, the pressure right here is also 0 in terms of gauge pressure. Okay, so take note in terms of gauge pressure. So this is 0. Then what else? And if this is let's say the point 2 is also exposed to the atmosphere, right? The point 1 is exposed to the atmosphere, because that's the free surface. Then the gauge pressure is 0. Then in the same way, if this outlet, all right, if this point is directly exposed to the atmosphere, then of course this will also be 0. And for selecting a reference datum, we said that we need a reference datum, right? So we can select, for example, if I want to select this as the reference datum, right? So let's say this is our reference datum. Then at that point, the elevation at point 2 with respect to that datum, this is actually also 0. Therefore, that's going to be v2 squared is just equal to 2g times the height at 1, right? z1. And therefore, the velocity can be solved using this equation, 2g z. Okay, so just take note about this reference line. So if you are going to make a reference line below, okay, so for example, this is our, okay, so for example, this is my reference line or datum. Then of course this will be, let's say this is my point 2 and then this is my point 1. Then let's just simply all right, another application is the measurement of flow using the piezometer and then the pitot tube meters. So for example, we have this pipe right here, a horizontal pipe, and if we want to measure the static pressure, then we can just tap a piezometer right here. And let's say this is our center line, and to measure the total pressure, we can just insert a pitot tube. Okay, so there's a fluid flowing inside. Then of course there's going to be a rise in here. Okay. Let's say this is the height of the fluid rise, and then for the dynamic or the total pressure, it's just gonna be, let's say, somewhere in this height. And if we want to measure the velocity, the velocity at this point. Let's say this is point 1, and then this is point 2. Then let's say this is our height. Right, for height 1 or z1, or no, not the z1. Yes, this should be the p1 by rho g. Then this one will be p2 by that's gonna be p2 by rho by rho g. And I guess this should be from this surface, from this height to I guess this should be to this center line. And again, this also at point 2, this should be to the center line. Okay, so we have also z1 right here at point 1. Of course, that's gonna be present. I mean, just in terms of writing the terms. And we'll also have v1 squared all over 2g right here. And here we'll also have v2 squared all over 2g, and we'll also have the elevation head at point 2, referring to elevation head at point 2. Now, if we want to apply the Bernoulli's equation, then we have p1 by the unit weight plus the elevation head, okay, plus what else? The velocity head, v1 squared all over 2g, is equal to the pressure head at point 2 plus elevation head at, right, this should be 1, then this one is 2, plus v sub 2 squared all over 2g. Okay, so just like what we did in the bank applications, then there are also we can also simplify the expressions by finding some terms that are zero. For example, we have the point 1 is at the same elevation as the point 2, and therefore z2 minus z sub 1 is just 0. Therefore we can just cancel this term. Okay, so this is also possible for, this is also applicable for other applications. As long as you have the same elevations, then the elevation head term would just be 0. Now what else? Now this pressure 1 divided by the unit weight, this is just actually equal to this height, right? So recall that we are in a head form, therefore this is just equal to the height. Okay, and for v1 squared, okay, so v1 squared, that's what we actually want to find. That's the velocity of the flow. And at point 2, we'll also have h, no, not h, or sometimes they just write it as h2, and sometimes this is h1. So that depends upon the notation, but the important thing is this refers to the pressure in these measurement devices. Okay, and for the v sub 2 squared all over 2g, now if you have this P2 tube, the assumption is that in this stagnation pressure point, or stagnation point, so it just simply means that the moving fluid is brought into rest, and therefore the velocity here is 0. Therefore this is also 0. And if this is in terms of height, then we can just write v1 squared all over 2g is equal to p sub 2 all over rho minus p sub 1 all over rho. And therefore if this is in terms of height, then that's gonna be delta h, right? 2g delta h, and take note this delta h refers to these terms, not the elevation head. Okay, so there are still other applications of the Bernoulli's equation, but I guess the effective way is to solve problems regarding the use of this Bernoulli's equation. Okay, so for the problem, we have our first problem for the Bernoulli's equation. The problem says a large tank contains water at a depth of 3 meters. A tap is installed at 2 points as shown in the figure. Determine the velocity and the water at the tap if it is open. Okay, so the figure, we have a tank, a large tank, and we have a tap right here. So if this, let's say if this one is open, then what's going to be the velocity of the water? If this tap is open, this one is closed, then what's going to be the velocity of water? And the figure, the problem also gives us the height from this reference line. From the free surface. So that's 2 meters and then 3 meters. Okay, so for the solution, okay, so let's try to find first the velocity at B. Find VB. Okay, and assuming P as the reference point or the reference line. Okay, so let's write down our Bernoulli equation. P1 all over unit weight plus z sub 1, or let's just write in terms of A, and we'll write here using A and B, point A and point B. Okay, so this is A plus the velocity at A all over 2g is equal to the pressure head at point B plus the elevation at point B plus the velocity at point B squared all over 2g. Okay, so this point 1 is actually exposed to the atmosphere, and therefore the pressure at point A is 0. Okay, the elevation, we have the elevation. Okay, so we'll just leave this term. And for the velocity, recall that the assumption is if we have a large tank, the area or the cross-sectional area or the diameter is way larger than the outlet diameter, then we can just assume that this velocity right here is 0. And for the pressure at B, okay, so since this is also exposed to the atmosphere, then this is just 0. And if our reference line is point B, then this is just also 0. Therefore, our equation would just be V sub B is equal to 2g times the elevation at A, the square root. So square root of 2 times 9.81 times the elevation at A with respect to B, that's just 2 meters. And that's 2 times 9.81 times 2. That's 6.27 meters per. Okay, so this is our velocity at B. Now we'll try to solve for find velocity at C. Okay, assuming C as the reference line, and we are considering points B and C. Okay, so we'll write again our Bernoulli equations. PB by, if you consider PB, I guess we need the pressure at B. So what if we'll consider point A? I guess it would be simpler if we'll consider A and C. Okay, so PA over rho G plus Z sub A plus PA squared all over 2G is equal to the pressure head at C plus the elevation at C plus the velocity head at C. And if you simplify, since this is exposed to the atmosphere, then in terms of gauge pressure, this is 0. In terms of velocity, the assumption is it is 0. And for this one, since this is our reference line, then this one is 0. And this is also 0 because it is exposed to the atmosphere. And therefore, our V sub C is just the square root of 2G times the height with respect to the reference. Okay, so 2G times, so instead of using the 2 meters height, we'll use the 3 meters height. Okay, so 2 times 9.81 times 3. Okay, so that's 2 times 9.81 times 3 square root. That's 7.67 meters per second. So what this means is that we have a faster velocity. We can have a faster velocity if we have a higher depths of fluids, meaning higher pressure. Okay, so I guess this is just a pretty straightforward example, and in our next video we will do some more problems regarding the Bernoulli's equation.